Hello students, welcome to another tutorial on heat measurements. In this video, we are looking at a glass that contains 0.25 kgs of water initially at 25 degrees Celsius. Now what we're trying to find is the amount of ice that is initially at -20 that must be added in order to obtain a final temperature of 0 degrees Celsius with all the ice melted. Okay, so here we're being taught to neglect the heat capacity of the glass. That kind of simplifies our problem a little bit. So we'll use the same technique we used previously. The only difference here, of course, is not really the difference, literally the same thing. The mixture will end up with the same temperature at 0 degrees Celsius. So we observe one thing again. We have two parts. We have a glass that contains water. So if this is our solution, so what we have is the heat that is going to be lost by the water, because water drops from 25 degrees Celsius to 0 degrees Celsius. So we have the heat lost by the water. We're going to find this using M, the mass of water, specific heat capacity of water, the change in temperature for water. So this is lost by the water. And then the next part, we notice that where is this going? The heat lost by the water is going to melt the ice. Now, ice is solid, so we notice one thing. First, it has to change from -20 degrees Celsius to 0 degrees Celsius. So we have the first one for ice. I'm going to say Q ice. Yeah, so Q ice. I could say this is the first one. This changes the temperature from -20 to 0 degrees Celsius. So this is going to be obtained by the mass of ice, specific capacity of ice, multiplying the change in temperature. And then after this, we have Q2, the second, this of course is gained. So I can say gained as the temperature increases from -20 to 0 degrees Celsius. So this is gained by the ice as this change is happening. And then lastly, Q2. So this is still ice, but now this is change of state. Now, because the question is saying that till just when the ice melts. So since it's change of state, we have the mass of ice and the latent heat of fusion of ice. Okay, so this is gained as ice changes state. Okay, so with that in mind, we notice one thing again. So you can, if you want to take note of that final temperature, initial temperature when dealing with this so that it gives you negative, you can work it out like this: Q1 plus Q2 plus Q3 is equals to 0. But I prefer just, and it's up to you. So if you use this, you can stick to final temperature minus initial temperature. And then if it gives you a negative, you see that when it processes, the equal sign to become positive. But for me, I always go with heat lost is equal to heat gained. So in this case, if you're going to use this method, change in temperature is no longer final temperature minus initial temperature. It's just the difference, whether positive or negative, just the difference in the temperatures. So of course, what is lost? We notice that the water loses. So Q water loses, and that is equal to Q1 for the ice during the increase in temperature plus the one gained by the ice during change of state. So from here, we have the mass of water, specific capacity of water, the change in temperature for water, equal to, this is during the drop, the increase in temperature. So it's the mass of ice, specific capacity of ice, the change in temperature plus, so of course this is for ice, this is for water, and then this is plus, this now was during change of state. L fusion of ice. So from here, we want to find the value of Mi, so I can factor it out. So now I have M water, C water, changing T for water equal to Mi. And then now I have Ci, changing Ti plus Lfi. So of course here I can substitute. So the mass of water, I mean, this is 0.25 kgs. Specific capacity for water, that's 4190. Change in temperature. So again, don't mind whether it's in kelvins or degrees Celsius. The difference is going to be the same. You can try to convert to kelvins and then get the difference to give you 25. So that's 25. This is equal to the mass of ice. And then now this side we have specific heat capacity of ice multiplying the change in temperature again. It's going to be 20 because change in temperature for ice, what you're looking at is we have, it comes to 0 degrees Celsius minus it's coming from 20 degrees Celsius. So this is going to be 20. That's the change. Okay. So here you have that change in temperature plus the latent heat of fusion for ice. That's 3.34 by 10 to the power 5. So if you simplify this, you notice that what you get is 26187.5 equal to the mass of ice. And if you simplify what is in the brackets here, you get 376,000. Divide both sides by this factor. You notice that what you end up with is 26187.5 divided by 376,000, giving you what Mi is. So therefore, Mi will be equal to 0.07. This is in kgs. So we can conclude that this is just 70 grams. Okay, so this brings us to the end of this question. I hope you guys were able to follow through. So just to help you guys practice, I found an exam question based on the same principle. So you guys can try it out, see how easy it will be. So in the exam, this question carried a few marks. I think it carried about up to 10 marks. So you guys can try out this question. So otherwise, after you guys are done with this, I think this is the last video we'll be doing in this series. Unless if I get any suggestions from you guys. In the next video, we're going to start looking at thermal expansion and see how it happens and how to determine certain quantities to do with that. Okay, so this was your tutor. We'll see you guys in the next video.